So this is the final presentation for group SD2101 for Jeff Godfrey and Abdullah Salami. Our project is the DC-powered three-phase induction motor variable frequency drive. Here are just some examples of the typical variable frequency drive operation. Instead of the step-up transformer here, we're going to have a boost converter. And the rectifier here is actually going to be a three-phase power inverter. And here we've got the three-phase squirrel cage induction motor as well. So the goal of the project is we're going to have a lithium iron phosphate battery pack. This is going to be lithium iron phosphate cells arranged in an array such that we have 16 in series, 2 in parallel, for a total of 32 cells. This should give us 51.2 volts DC at 12 amp hours, or 12,000 milliamp hours, as they like to explain it. Here we've got the boost converter. We want about 330 volts, or 330 volts output. I am looking at replacing this diode here, which would typically be a Schottky diode, for a PMOS to just increase the efficiency a little bit, and it would only make up for that voltage drop across the diode, so we're still kind of looking at that. Here we've got the power inverters, motor. So the overall topology is we'll have a rechargeable battery pack, lithium iron phosphate solution, and then we'll have the boost converter circuit that will boost it up from that 51.2 volts to that 330 volts, and then we'll have 3 power inverters. And what that'll do is it'll make 3 different signals 120 degrees out of phase for our 3-phase induction motor, which should be 210 volts RMS. That will drive the induction motor, which will have an encoder, so we'll have a motor controller via this microcontroller here. Still uncertain if we're going to use one microcontroller for all of the control signals, or individual controllers for at least the boost converter circuit, and then for another one for the inverter and induction motor. So the user will control the speed, most likely via potentiometer. We'll have a voltage and current feedback from the boost converter to the microcontroller, which will then go and control what will be the duty cycle of the MOSFET included in the boost converter. Then we will have our PWM control signal, which this will be PWM as well, going to the boost converter. Then we'll have actually 3 separate PWM signals going to the 3 power inverters, and this will get our 120 degrees out of phase output signals, which will be on the inverter duty cycle. Then we'll get our phase, frequency, amplitude feedback from the inverter. That way we can tell where we're at, if we need to adjust the speed. If we see that the motor is running slower than our desired speed, then we'll have that feedback, which will take the current phase, frequency, and amplitude feedback and adjust it accordingly, which will probably, I believe, be through the frequency. So for the project requirements, our battery pack needs to be able to support at least 600 watts of power and output at least 50 volts, approximately 50 volts. It has the capacity to output 600 watts for 30 minutes. These are just the bars that we've set ourselves. Of course, we expect to do better than this. The battery pack must be rechargeable with a fused output. Must be equipped with a BMS, and this will actually more than likely be 2 BMSs, which I'll explain later. These will control over overcharge and discharge protection, short circuit protection, balanced charging and discharging, and we'll have indicator LEDs for the battery pack that will identify on, off, or charging. And then, so we did decide on lithium iron phosphate battery solution, 16 series 2 parallel. BMS, I haven't really begun to look at that. That is something that I'll also explain later. The protection circuitry will be through the BMS, and I'll explain that later. For the motor, the requirements are a 3-phase squirrel cage induction motor rated at half horsepower at 230 volts RMS. I said 210 earlier, I meant 230, 330 peak. Originally, we had started off with we wanted to power 1 horsepower squirrel cage induction motor. What we realized is that those are not as common as either half horsepower or 1.5 horsepower. So we made the decision to cut it down to half horsepower since the application would be a kayak trolling motor. Half horsepower is honestly way more than enough. Typically, they run at 0.2, I believe, to 0.4 horsepower, or 0.3 to 0.4 horsepower. So the motor must be rated inverter duty. That's because we are doing a DC powered induction motor, and so we'll have that approximated sinusoidal wave, that approximated DC output, but it'll be inverter duty. It's all created through pulse width modulation. So it'll be an approximate, or it'll be an average value of the voltage that'll be taken as an approximated sinusoid, or AC. So it must be capable of being driven at least 400 hertz. It must be equipped with an encoder, and that'll give us our feedback loop to the controller with the phase, amplitude, and the motor must be totally enclosed to machine. This part is more of Abdullah's expertise here. I haven't read up on the regulations, the NEMA regulations here. But it will be insulated and have appropriate, I guess, heat distribution. And it will be water resistant, not necessarily waterproof, but we'll look more into that. That's way further down the line. So we're going to utilize induction motors found in the lab right now. I believe it's the hallway of the power electronics lab. And then we'll kind of scale up from there. When we are able to scale up to an actual prototype, then we'll look at purchasing a motor that meets our specifications. So the boost converter needs to be able to support at least 600 watts of continuous power. That's approximately 50 volts at 12 amps with a lithium iron phosphate battery packs. It's difficult to get an exact output because each cell itself is different, and so it's more about the pack as a whole. Output at least 50 volts under full load conditions. Needs to be able to support potentially high motor starting current, 50 amps, and other transients. And this isn't just the motor current as well. This is also the boost converter. Boost converter typically, when it fires it up, and that inductor is trying to resist the change in current, or even as it builds that electromagnetic field and discharges, you get these spikes in amplitude. So we need to be able to support that, be rated for that. Should be at least 80% efficient, short circuit protected, reverse voltage protected input from the battery pack itself. We want 5 to 10% output ripple. We're still kind of working on that part. Dedicated kill switch, pretty much. It needs to utilize the closed loop control. So we should get the desired output and the actual output, and then we'll have a feedback loop telling us what the voltage and current is at the output, and adjust the duty cycle of the signal going to our MOSFET accordingly. I'm still working on that design. The boost converter and the battery pack are my tasks in this project. So it needs to, the inverter needs to be able to support 600 watts of continuous power, 330 volts, peak 600 milliamp per phase. It needs to be full bridge, not half bridge. So we don't want a half rectified signal. Method of the generated sine wave output will be sinusoidal PDM. So that's the that inverter duty cycle rated motor. That's why we need to have that, is because our AC is approximated. It's a DC output, but given in pulses of various duty cycles. And it's going to be a 3-phase output. Each phase should be 120 degrees out of phase. And this component as well should be at least 80% efficient, dedicated kill switch, and needs that closed loop control with the chosen motor. So we'll have the encoder on the motor that'll give us our actual versus expected, and then we can adjust the frequency, or we haven't tested it yet. Maybe you'll have to control the phase a little bit, but we'll get to that part. So for the microcontroller, this is something that we're discussing. I personally believe that the boost converter should have its own microcontroller. It doesn't really, we want a certain output voltage, and that's not something I don't think should be adjusted. It should be the signals themselves, like for the pulse width modulation for the MOSFET, for the boost converter, for example. That should be adjusted to increase or decrease output voltage accordingly. And I think that is kind of independent of the rest of the system. We have a bottleneck there. This is our 330 volts, and we want to make it 330 volts. And nothing else matters. The inverter needs to have 3-phase pulse width modulation integrated hardware module. Needs to have at least 2 input pins for encoder feedback. So that would be like the phase and amplitude of the signal. Needs to be capable of switching at least 5 kilohertz. And when we look at switching speed as well, for the boost converter, it seems to me that a lot of MOSFET drivers operate up to like 500 kilohertz. So as far as my simulations go, I've been looking at more of the 400 kilohertz area. So the user interface needs user interface so that user can adjust the boost converter output voltage, inverter frequency, and view on displays these parameters. That is something that will definitely be further down the line, and I'll discuss that later. So our budget, this budget was actually more around when we were planning for to drive a 1 horsepower motor. And so making the decision to switch to that 1/2 horsepower motor, first of all, we've got a more common motor, more easily found, therefore more competitive pricing, I would assume. And it's about half the price for the motor. So that's going to save us a ton of money as far as the motor goes. And not only that, but running at 1/2 horsepower is half of the source requirement. So that's half the batteries we need. Originally, we were looking at 16 series 4 parallel array. That would give us 24 amp hours because we're going to need more juice to drive, higher power. So that has cut our battery costs down, the cells as well as the BMS. Originally, we would have had to have 4 battery management systems somehow connected together. That's something I'm still kind of looking at. Now we're looking at 2 battery management systems, which can actually get pricey if you're looking for all the bells and whistles like protective circuitry and feedback. So other than that, our budget has remained fairly unchanged, but that is going to save us quite a bit of money. So this is the timeline for Abdullah. He goes above and beyond for sure. He's been doing quite a bit of academic reading here. He wants to get a variable frequency drive and kind of analyze it and see what's going on, how commercially I believe they work. He was talking about an old one that he saw at work. I know he had his eyes on. And then he wants to start off with a single phase and low power, get that um, breadboarded over the summer. Complete the report on selected motor, so actually picking out a motor that we want, designing an initial control system, so kind of that feedback loop that'll have to do with the microcontroller here. So we'll need microcontrollers for the interface, which that's going to be probably the last thing we do actually. We could select it, but actually programming that, first we want it to work, and manual control and whatnot, and then we'll get it all customer happy. So a microcontroller for the inverter, and I believe these are actually the PCBs here. That may be a little further down the road than what's listed here. So learn the basic use of the microcontrollers. That's definitely going to be very important if we're going to have an actual design here that has those feedback loops and can adjust itself accordingly. That's going to be a crucial component here, and it's going to take quite a bit of research. Then we're going to design the user interface and breadboard it by hopefully July, August. Have the schematic, PCB layout, and final testing of the user interface board by July 30th. This is for Abdullah. So this is his timeline for next semester. Complete all of his reading. I know he's got a stack of books going. Wants to have the battery pack made. I want that too. I'll discuss that later. Microcontroller user interface board completed. And then basic code, like pulse width modulations for controllers for the inverter or the power inverter and boost converter, and looking to get in that feedback loop set up. Was to complete his prototyping of the high voltage version by October. Get the schematics and PCB layout here, same in October as well. Check out all our PCBs, make sure that all of the traces are good, and actually build our first version. That's what Abdullah did so far. Completed reading of chapters 2 and 3 of AOE. Basic reading research of variable frequency drives, inverters, and battery packs. Completed his first LT SPICE simulation of the 3-phase inverter, which I looked at, and it looks pretty awesome. Completed his reading of the induction motor chapter, and we've both been talking with Jeff quite a bit, and get back to that later as well. The microcontroller, he worked through the basic use of the motor development board that utilizes this PIC that he's looking at. I know it's got a lot of PWM pins on it and registers, and research options for the inverter microcontroller, which I have not looked at yet. So this is the 3-phase power inverters. Well, three three-phase power inverters, each individual one here. As you can see, it kind of looks like an H bridge, and that's pretty much what it is. Except the pulse width modulation is significantly more complicated in calculating, the duty cycles, as well as making sure that these are each 120 degrees out of phase with each other, which he's done an excellent job with here, as you can see, and he's even got the flyback diodes here, so gorgeous. And that's the approximated wave here, and you can tell the duty cycle on the MOSFET driver here compared to the amplitude of our approximated AC output. Now, as far as what I did so far, I made a big mistake at the beginning of the semester. I got super excited about the battery pack and battery management systems, and I devoted a lot of my research time into that. I spoke with Jeff about this on a couple of occasions, and then he advised me that it would be a better idea to devote my time initially to the circuitry that's going to control the signal, like the boost converter and the power inverters. Um, so when we get the boost converter and the power inverter down or prototyped, we can test that easily through an external source like a function. You can use a function generator or a power supply. And then we have a plethora of motors available to us as well, from old projects and etc. We can find a cheap motor to, prototype with. So anyways, I've researched various cells and decided upon the lithium iron phosphate cells with a nominal voltage of 3.2 volts at 6,000 milliamp hours as far as cost to size to energy density to weight, overall weight. This seemed, and also availability. These are very common cells. This seems like the proper decision. After the project decision to switch from 1 horsepower to half horsepower explored the possibility of the 16 series 2 parallel array offering 51.2 volts nominal at 12 amp hours. That's approximate. According to this array decision, explored a solution with 2 prefab BMS systems, one for each parallel unit, and that way we get that balanced charging and discharging, short circuit protection, and overcharge discharge protection. The thing is, you want to make sure that every cell is accounted for in a battery management system, so that way you're going to have some weaker cells and some cells that are stronger than advertised. And so you want to make sure that, when one cell is completely charged, it doesn't stop those stronger cells from charging themselves. You also want to make sure you don't overcharge or discharge, because then you'll damage the lifetime of the battery. And I began to research methods of pack construction, the actual battery pack, to include the array. So there's a couple options. We can do the cells with the tabs and the screws, and then just put bus bars on top. So they'll have bolts that'll come out. Put the bus bar on top of that from one end of one cell to another. For instance, cathode to anode for a series connection, and then you just screw a nut in there, and they're good to go. The other solution, you can get cheaper cells that don't have screws or tabs or anything. You take nickel plate and you spot weld them on there. And a spot welder looks fairly cheap. You could buy one, I think, for like around $10 to $15, or even make one on your own. For the boost converter, I watched various media. I got caught in the rabbit hole that is do-it-yourself. YouTube and the Google net, et cetera, et cetera. So this very clearly is a mistake I made this semester, and it needs to be solidified by academic material. I also explored the option of replacing the Schottky diode in the boost converter with a PMOS, and feed them both the same pulse width modulation signal. So one will be on, one will be off, the other will be on, the other will be off, et cetera, et cetera. And that would just save us the voltage drop across the diode. And looking at the voltage that we're going to be operating at, I don't think that would be significant, but it's kind of cool to try and make it as efficient as possible. I began to attempt simulating the boost converter as well with various NMOS switches. And this is the problem that I have come across with the simulation. I chose an LT Spice library MOSFET, not the generic one. I chose a different one. But after going through a few of these, thinking, well, my on resistance seems okay. My VDS max, voltage drop from drain to source, seems fine. One thing I noticed that it doesn't include is the continuous drain. So the current to the drain, continuous drain current, is not listed on the SPICE library components. So earlier tonight, I was actually looking at importing a new component and looking for something that has that that current accounted for and modeling it in SPICE and seeing if that fixes it. But most certainly, I need to read more academic material on this. I can't just be YouTubing how to build an efficient boost converter. So I'll be looking into that over the summer. Now, I didn't get the voltage I wanted out of this. I've got 51.2 volts. You see this blue line here, that's my VN. And then I've got the switch voltage. So the voltage at the drain of the MOSFET. And as you can see here, the voltage increases slowly, and it kind of correlates with that switching, right, of that MOSFET you can see here. This is the current through the inductor of the boost converter. Again, this is what something I had mentioned earlier but you have this huge spike of current going through that inductor when it first starts. And I know that there's a similar thing that occurs when you shut off the system and the motor, I forget what it's called. It's in flood or in current or something like that. But you'll see a huge spike in current delivered by the induction motor when you shut the system off. So that's why we want reverse protection as well. But again, you can see the current of the inductor is correlated with the switching of the MOSFET. And here's a closer look at that. In the blue here, we have the gate voltage of the MOSFET, and you can see it's a relatively large duty cycle. I believe it's the period is 2.5 microseconds, and the duty cycle is T on. The on cycle is 2.125 microseconds. So it's really actually kind of exciting to look at on a closer level to see the things that you've read about actually kind of work. So you see as I didn't really explain exactly how this works here. So let me open this back up. So what happens with the boost converter is when this MOSFET is on, it acts as a switch. And so your source goes through the inductor and has a path going straight to ground here. The inductor does not like that change in current. So what happens is it starts to build up an electromagnetic field. When this switch is off or open, it discharges this current across this diode, the Schottky diode. I believe this one's rated for 600 volt breakdown. And so then it comes across that diode over here where it charges the capacitor. Now, you would think, okay, if this was closed, right, we have the, approximately 0.7 volt drop here, we should be at, that would be 50.5 volts here, right? What happens is that voltage will charge up this capacitor, and then when this closes again, or your NMOS is on, and that inductor charges up even a little more. So then it pushes up when this is open again, pushes that current through, and it ups the voltage on this capacitor, right? So eventually you get a step up. Here's that current again. And then you see as it's turned on, the current starts to just build up, and that's turned off and it discharges. And on, it builds up, discharges, builds up, until eventually you get where it kind of reaches almost an equilibrium at a certain point. Okay, so the next steps for Abdullah, reading chapter 4 and 6 of AOE. I know he's got a lot of reading that he wants to do. For the inverter, purchase a VFD, variable frequency drive, to analyze it, and analyze microchip motor development boards like the PICDEM MCLB. I'm not familiar with that one yet. We haven't discussed that. The motor, look through motors in the lab and select one as our project motor. I did notice a lot of them, I believe, were 120 volt, but we can always scale that if we learn how to control our feedback loops. For the microcontroller, select and purchase microcontrollers and begin learning to use them. For the battery pack, read through do-it-yourself lithium battery book. I've been doing a lot of DIY lithium stuff, and I'm probably going to be looking at a more academic-based approach because there's a lot of cool stuff out there and it's easy to get lost. For me, I want to begin reading more, like I said, academic-based literature on boost converters, mainly in regards to picking an NMOS. Again, I believe it comes down to that continuous drain current, and that just, I need to be able to properly model the NMOS that I want, and I think it'll work. Implement a smaller scale boost converter on a breadboard, and instead of having a microcontroller for the PWM for the MOSFET, I'll start off with a function generator just to see if I can get the behavior out of the boost converter that I want. Find an ideal microcontroller for the PWM or a MOSFET driver, and then research the best way to prototype high power electronics safely and efficiently. You know, it's funny, there's not too much information from what I can see on this on the internet, how to safely work with power electronics and make sure that you don't destroy the equipment that you're using that's thousands of dollars. So this might include, I spoke to Jeff before, you know, he said that working with dangerous levels of electricity, obviously we're going to have to need some kind of safety protocol. So this summer I'd like to get together with him and hash something out so we have the blessing to proceed and test. Goals for the summer for Abdullah: complete reading and background prep, the user interface board, get the battery pack done, low voltage version of circuits, simulated breadboarded and tested, and the motor selected and report made. For me, I wanted to pick the appropriate MOSFET for my simulation to make sure I know the behavior that's going on. Breadboarding a scaled down version, probably be 5 volts to like 32.2 volts to see if I can achieve that accurately. Research an appropriate microcontroller for driving a MOSFET and interpreting, adjusting to voltage current feedback from circuits. So it's got to have pins. It's probably going to be an ADC pin on the microcontroller as well. So, and then implement the microcontroller in breadboarded scaled down version of the boost converter. My assumption is that most microcontrollers we're going to be feeding 5 volts to power it for our VDD, and so we're going to have an output 5 volts. So I think we should be able to use the same microcontroller for a scaled down version as a scaled up version, but I'll have to look into that further because there might be certain current restrictions that a voltage regulator won't be able to take care of. So I'll look further into that. So that is our project. I also wanted to share, nope, it's not on there. Okay, that is our project. Like I said, unfortunately this semester has been a little tied up with signals and systems and trying to find time to work on this project, but now we've got all summer, so we're going to get something done. Thank you very much.